In this lecture, we're going to do 4 examples of solving problems with lines and planes. 2 of them actually have 2 questions embedded, so it's really like 6 examples. So first, we'll find a vector equation for the plane that contains the point P and a line whose parametric equations are given. In our second example, we'll find a point of intersection for 2 lines which do intersect. Of course, they don't have to intersect in R3, but we'll find where these 2 lines do intersect. Since they're intersecting lines, they determine a plane. So then we'll find the plane that contains those 2 lines. Our third example will find the distance from a point to a line. And then in our fourth example, we'll find the angle of intersection between 2 planes. We've seen how to do that. Since the planes intersect, they determine a line. So we'll finish that example by finding the line of intersection. Okay, so let's get started on example 1. We would like to find a vector equation for the plane that contains the point 1, -3, 0, and the line whose parametric equations are x equals 3 minus 8t, y equals -3 plus 5t, and z equals 2 plus 2t. I recommend always beginning these kinds of problems by sketching a picture so that you see what information you have and what information you can deduce from it. So let's say this is the line we're given, and this is the point P. Of course, we couldn't solve the problem if the point P was on the line, because a line does not determine a plane, but it turns out that P isn't on this line, thank goodness. So P is out here. I'll just label it as 1, -3, 0. And then we have a line. From the parametric equations, we get 2 pieces of information. There's a point on the line that we can identify. For that, you could plug in, say, t equals 0 and see that the point 3, -3, 2 is on this line. That's an immediate thing that you can read off of the parametric equations. Of course, you can plug other values of t into these equations to pick up other points. All right, so let's say q is down here. You might not need it, but it is a piece of information that we get for free. Another piece of information we get for free is the direction vector. So the direction vector is -8, 5, 2. Those are the coefficients in front of the t terms in each of the scalar parametric equations. So that tells us that we can think of that vector v as living on this line. Right, so a vector is a direction and a magnitude. It's not anchored to a point in space. So here I have a vector whose direction is parallel to this line. So we can just move it onto that line and think of this vector as living on this line. Now we ask ourselves, what do we need in order to write down the vector equation for this plane? Well, first we need a known point. We have this, we can use P. And we need the orthogonal direction given to us by some orthogonal vector n. So we need to find this vector n. To do that, what I'm going to realize is that from my line and my point off to the side, I can find another vector which lives on this plane but which doesn't live on the line. That way, when I take the cross product of this new vector, in fact, it's the vector QP the way I've drawn it, with the vector QP and the direction vector V, we can take the cross product and that will give us the orthogonal vector n. So first of all, what is QP? It's the coordinates of P minus the coordinates of Q, so that's negative, let's see, what am I doing here? 1 minus 3 is -2. -3 minus -3 is 0. 0 minus 2 is -2. Did I do that right? Yes, okay. All right, so let's say that n is QP, one vector from the plane, cross V, another vector which lives on the plane. So we can say I, j, k along the first row. Let me write QP on the second row, so -2, 0, 2, -8, 5, 2 along my third row. I cross these and I'm going to get in the first coordinate -10, -12, -10. So we have found that the direction which is orthogonal to the plane we're looking for can be described with the vector -10, -12, -10. But that's kind of a weird vector to use here because we could divide it by -2 just to make it a little bit nicer, and that vector would still be orthogonal to the plane. So in fact, for simplicity, let's use 5, 6, 5. 5, 6, 5 is parallel to -10, -12, -10. So therefore, it's also going to be perpendicular to the plane. All right, so our vector equation is 5, 6, 5, that's the orthogonal vector, dot the vector difference x, y, z, minus our known point 1, -3, 0. That is a vector equation for this plane. Any point on the plane has x, y, z coordinates that make this equation true. If you wanted to, you could expand this to find the general form. Now what you can also check is if I used -10, -12, -10 here, or I used q instead of p in the second part of this equation, and you expand it, you will get the same general form after simplification. So while there might be a lot of different ways to write down a correct vector equation for the plane, the general form after simplification is much less ambiguous. In our second example, we have two questions here. So we want to find the point of intersection for two given lines, both given with the vector form of the line. And then since those lines actually do intersect, we can find the plane that contains those two lines. So there's exactly one plane containing two intersecting lines. Assuming, of course, that the lines are distinct. So if you think of a line as intersecting with itself, then that doesn't uniquely determine a plane. But here we have two distinct lines which are intersecting. Okay, to tackle this problem, what I'm going to do is take these two lines written in vector form and convert them into scalar parametric equations. So for my first line, I have x equals 2 minus t, y equals t, and z equals 1 plus t. For my second line, I'm going to write out the scalar parametric equations, but I'm going to switch the parameter from t to s. And the reason why is, let's say that this point here is the point 2, 0, 1, and this point here is the point 4, -5, 8. So those are the 2 points that we can immediately identify. So from 2, 0, 1, I know that this point is on this line, and from 4, -5, 8, I know that this point is on the second line. What we're looking for is their point of intersection. Now t is what traces us along the line. So it might be that for a t value of 1, we get to that point according to the first parametrization. But for a t value of 10, we get to this point via the second parametrization. T is really acting independently in these two equations. So we can't think of this point of intersection as happening for the same value of t. So therefore, I'm going to switch from t to s just so I understand that t might behave a little bit differently in these two equations. So this point might happen for a t value of 1 for the first equation and a t value of 10 for the second equation, and I might arrive at a problem if I try to describe both equations with the same letter t. So, okay, so I'm going to switch to s for my second equation, and we'll have x equals 4 plus 2s. Got to take my own advice. Y equals -5 minus 3s. Z equals 8 plus s. At the point of intersection, the x, y, z coordinates on the left-hand side will be the same. So what we're looking for are the coordinates x, y, z at the point of intersection, so they're the same. So what that means is that the right-hand sides must also be the same at that point of intersection. In other words, I have 2 minus t must be equal to 4 plus 2s. I have t must be equal to negative 5 minus 3s. And then I have 1 plus t must be equal to 8 plus s. This is 3 equations for 2 unknowns, so you don't even need all 3 to solve for this. Pick your favorite pair, and then you're solving a system of 2 equations for 2 unknowns. So let me pick the second one, seems nice, and let's use the third one. Okay, so here, the second one tells me that when these 2 lines intersect, t, the parameter for the first equation, will take the same value as negative 5 minus 3 times the parameter for the second equation. So let's substitute that in to the third equation. So we're going to get 1 plus the substitution we make. So instead of t, let me write negative 5 minus 3s equals 8 plus s. Now we just solve for s. So let's see, 1 minus 5 is negative 4, minus 3s equals 8 plus s. So 4s equals negative 12. So this tells me that s equals negative 3. Back in the second equation, just try to keep my work a little bit separate here. T is going to be negative 5 minus 3 times the value of s we just found, which is negative 3. So we get t equals 4. Okay, let's check that. If I plug 4 in for this parameter, what point do we get on the line? We get 2 minus 4 would be negative 2. 0 plus 4 would be 4. And then 1 plus 4 would be 5. So the first line suggests that the point of intersection should be negative 2, 4, 5. Let's check that with the second equation. For this one, I want to plug in a parameter value of negative 3. 4 plus negative 3 times 2 is 4 minus 6. That's negative 2. So far, so good. Negative 5 plus 9 would be 4. Okay, that works. And then 8 minus 3 is 5. Great, we did it. So the point of intersection for these 2 lines is the point negative 2, 4, 5. Okay, let me erase what I don't need in order to solve the second part of the question. So let's find the plane that contains these 2 intersecting lines. In this diagram, I have a lot of good pieces of information. I have 3 points. We know that 3 points gives us a plane. But I also have 2 vectors that we know live on this plane. We have the vector negative 1, 1, 1. We can think of that as this vector right here. So since this vector points us along the line, we can imagine it as lying on this plane. And similarly, we have the vector 2, negative 3, 1. So we can think of the direction vector 2, negative 3, 1 as lying on that line and therefore is lying on this plane. So this was 2, negative 3, 1. We need a point and a sense of direction in order to find the plane that contains these 2 lines, but we're good because we have 3 points we know, and with these 2 vectors we can cross them to find the orthogonal vector. So n will be negative 1, 1, 1 cross 2, negative 3, 1. So that's going to be I, J, K on the first row. Negative 1, 1, 1, 2, negative 3, 1. We do this cross product and we get 1 plus 3 is 4, 3, 1. That's an orthogonal direction for this plane. So the vector equation of this plane would be the dot product of 4, 3, 1 and the vector difference x, y, z minus, pick any point you like, how about p, so 2, 0, 1 equals 0. Let me put it in general form. If I do that vector subtraction and take the dot product with 4, 3, 1, I'm going to have 4 times x minus 2 plus 3 times y minus 0 plus 1 times z minus 1 equals 0. So 4x plus 3y plus z equals, let's see, and then my constant on the left-hand side was going to be -8 minus 1 is -9, so 9 when I move it to the right-hand side. So that would be the general form for this plane. Now for this third example, we're looking for something a little bit different. So in this example, we want to find the distance from a point to a line. So as usual, let's start by sketching the scenario that we have. So we have a line and we have a point. Our point is 2, 1, 3. And the line is 1, 0, 1 plus t times -1, 3, 2. That tells us that the point 1, 0, 1 lives on this line. So let me call that Q and I'll label it here. And our sense of direction along the line is the vector, let me call it V, equals -1, 3, 2. If we're looking for the distance from the point to the line, we are looking for the shortest possible line segment that would connect the point P to a point on the line. So this line segment I've just sketched will be perpendicular to the line. Okay, so here's the configuration that we want to understand. And yes, there is a formula for this calculation, but I would rather set it up and solve it with geometry than just memorize a formula. It's always great to understand where the formula comes from, or even better to be able to rederive it. Okay, so we have a vector, we have a point out here, and we're looking for this line segment perpendicular to the vector and connecting us out to the point. Hopefully this configuration reminds you of a topic we've already seen, which is vector projection, and also orthogonal decomposition of one vector with respect to another. So in particular, let me create the vector QP. We know the coordinates of this vector are 1, 1, 2, because it's P minus Q. And then what we realize is that this length that we're looking for is really QP perpendicular if QP has been orthogonally decomposed with respect to V. So recall that the vector QP can be written as the vector sum of QP parallel, that would be the projection of QP onto this line, plus QP perpendicular. So that tells us that QP perpendicular is QP minus QP parallel, which is QP minus the projection onto the vector V of the vector QP. So we'll compute this perpendicular component and then we'll take its length in order to find the distance. So let's see, QP itself is 1, 1, 2 minus, and then the projection of QP onto V is going to be the dot product of QP with V divided by V dot V times V. Okay, let me give myself a little bit more room. So that's going to be 1, 1, 2 minus -1 plus 3 plus 4, so 6, divided by 1 plus 9 plus 4, so 14, times -1, 3, 2. Let's see, 6/14 is 3/7, so maybe that'll make it a little bit nicer. And then we have 7/7 plus 3/7 is 10/7. 7/7 minus 9/7 is -2/7. Then 14/7 minus 6/7 is 8/7. Okay, so that's the perpendicular component in the orthogonal decomposition of QP with respect to V. That's the vector that takes us from the line to the point. So the distance from the line to the point is going to be the length of that vector. Okay, before I compute the length, let me factor out 2/7, and we're left with 5, -1, 4. So that's positive scalar of 2/7 will stay in front of the length computation, and then we're left with the square root of 25 plus 1 plus 16. So we get 2/7 times the square root of 42. So that would be the distance from the point to the line. Again, there is a distance formula that you could memorize, but there's enough things to memorize in life. I really encourage you to try to resolve this problem right now, where you draw the picture, fill in the right triangle, and then recognize that the legs of this right triangle are QP parallel and QP perpendicular. And then realize that the distance from this point to this line is just the length of the perpendicular component. All right, we've reached the last example in this lesson. So let's find the angle of intersection between these two given planes, 3x minus y plus 6z equals 10, and x plus 2y minus 5z equals 0. We'll find the angle of intersection, and then as a separate question, what we'll do is we'll find the line of intersection. We'll actually do that two different ways. Okay, so in a previous lecture, I sketched this picture, and that will work here as well. So we have two planes. Let's say this one on the left is 3x minus y plus 6z equals 10. And the one on the right is x plus 2y minus 5z equals 0. The angle between these two planes is equivalent to the angle between their orthogonal vectors. For each of these planes, they're written in general form, so we can read the orthogonal vectors off of the coefficients of the x, y, z terms. So the orthogonal vector for the plane on the left, 3x minus y plus 6z equals 10, is the vector 3, negative 1, 6. So that vector points in the orthogonal direction to this plane. For the other plane, a vector orthogonal to that plane would be 1, 2, negative 5. The coefficients of x plus 2y minus 5z equals 0. We know how to find the angle between two vectors. We use the dot product. So we can say that cosine of the angle that we're looking for is 1, 2, negative 5 dot 3, negative 1, 6 divided by the length of 1, 2, negative 5 times the length of 3, negative 1, 6. Okay, so in the numerator, that dot product is going to be 3 minus 2 minus 30. And then we have divided by the square root of 1 plus 4 plus 25 times the square root of 9 plus 1 plus 36. So that's going to be negative 29 divided by the square root of 30 times the square root of 46. So that's going to be, let's see, since both of those numbers are even, we can factor out square root of 2, square root of 2, that gives us 2. So we'll have negative 29 divided by 2 times the square root of 345. Okay, so the angle between these two planes is the arc cosine of that number. So we want to compute the arc cosine of negative 29 divided by 2 times the square root of 345. And if you do that, you get approximately 2.47 radians, or 141.32 degrees. That means we actually found the larger of the two angles. So the angle between these two planes, if I do it in degrees, we get 38.68 degrees. So if you imagine the ways that two planes could intersect, if you look at this X shape over here, either the planes are orthogonal in which case the angle they form is 90 degrees, or one will be acute and one will be obtuse. So our calculation returned the obtuse angle. To find the acute angle, we just found its supplement. So 180 minus theta gave us the angle between these two planes. Okay, we now know that these two planes intersect at an angle of almost 40 degrees. Let's address the second part of this problem, which is to find the line of intersection. That's this line I've sketched here. We'll do this two different ways. So first let me erase what we don't need. We don't really need this angle anymore. Our first method will be to find 2 points that must be on this line. There are infinitely many points that live on this line. I just want to find 2 of them. So what I'm going to do is solve for x in the second equation. We see that x equals negative 2y plus 5z. Now let me plug that expression for x into the first plane. We'll be left with one equation for 2 unknowns, y and z, and then we'll figure out how to extract points out of that. So we have 3 times the expression negative 2y plus 5z minus y plus 6z equals 10. Let's combine like terms. So we have negative 6y minus y is minus 7y. 15z plus 6z is plus 21z equals 10. This is now a line in the yz plane. It's just a line, we just need 2 points off of it. So I could, for example, set y to be 0. This tells me that z would be 10 over 21. And then if I return back to star, x would be negative 2 times 0 plus 5 times z, so that would be 50 over 21. Then I could set z to be 0, and we get that y is negative 10 over 7. And returning back to star to find x, we get that x is negative 2 times y plus 5 times 0, so that's 20 over 7. So now we have 2 points that live on this line. We can now find the direction vector by just subtracting the coordinates of one point from the coordinates of the other. Okay, let me give myself some more room. So our direction vector v for the line, we can do 20 over 7, negative 10 over 7, 0, minus 50 over 21, 0, 10 over 21. That leaves us with 10 over 21 in the first coordinate, negative 10 over 7, and then negative 10 over 21. So this line in vector form is r equals a point we know, so let me pick 20 over 7, negative 10 over 7, 0, plus t times 10 over 21, negative 10 over 7, and negative 10 over 21. And yes, you could come up with a nicer direction vector, but this is fine, so this would be the equation of this line. Let's solve that problem again. So we'll find the line of intersection using method 2, which is to find one point and the sense of direction for the line. We would find the point using the method that we just used. So let me carry over the fact that the point 20 over 7, negative 10 over 7, 0 was on the line. No need to refine that point. We would like to find the vector now that points along the line. What has to be true about this vector is it has to lie on both of these planes, which means that this vector is simultaneously orthogonal to the vector 3, negative 1, 6, and orthogonal to the vector 1, 2, negative 5. So to find that vector, let's take the cross product. So v is going to be 1, 2, negative 5, cross 3, negative 1, 6. Okay, so I'll do this cross product pretty quickly. So after crossing them, we're left with the vectors 7, -21, -7. More simply, let's use the parallel vector 1, -3, -1. You can check that the vector that we found in the previous method was actually parallel to this vector. So we found the vector 10/21, -10/7, -10/21. That's actually also parallel to 1, -3, -1 because it's the same direction. Okay, so now our line is r equals the point we know, written with its position vector, so the vector 20/7, -10/7, 0, plus t times 1, -3, -1. It looks different than what we found with method 1, but it's the same line. So it's the same point, and it's the same sense of direction. So it'll trace out the same points in R3. Okay, I hope these 4 examples gave you a good idea of how to work with lines and planes, especially when they're mixed together. Thank you for your attention.